everyone to the GADEP seminar. So today we're very happy to have Pepin Lehalleur, who will speak about exponential periods and exponential Voevodsky motives.
Thanks a lot for the invitation. So I can still hear myself. Is everyone muted or? Yeah. Okay, so I will talk about no.
Well, you have 3 different accounts, so maybe.
No, you were muted, Simon.
Simon, you are muted.
Okay, so now I can hear myself. Okay, maybe I will just do this, and when you ask question, I will have to put it back because otherwise it's really not possible. I'm really sorry about this technical problem.
Maybe for the question we will put in the chat. Okay.
Joint work in progress with Javier Fresãand Martin Gallauer. So let me start with a little schematic of the theory of periods and motives, and just to situate where I'm talking about. So I mean, there's this the way I think about this picture of periods and motives is with this at least three levels of let's say concreteness or an abstraction, or examples and formalism, or computation and conjecture, or phenomena and structure. So the first level would be the level of periods themselves and how we can obtain relations between periods from algebraic cycles. Then the second level would be the cohomological one, the cohomological interpretation of periods via the comparison isomorphism between Betti and the Rham cohomology. And there the relations between periods are given by classes in Charles groups and via the cycle class map. And then there is a level of motives, so of mixed motives, which can mean either Nori motives or Voevodsky motives. And there the relations between periods are encoded in the action of motivic Galois groups on period torsors. And so even though this talk is very much about this third level, so about the Voevodsky motives, so in the context of this generalizations of periods called exponential periods, I will to motivate what's going on there, I will have to talk a bit about the whole picture in this exponential setting. So roughly speaking, I mean, in this seminar, I assume that most of you know the definition, but so period is roughly speaking are complex numbers which are obtained by integrating algebraic differential forms on algebraic varieties defined over number fields. And exponential periods are also, roughly speaking, are complex numbers defined by a similar procedure, but instead of integrating algebraic differential form, we integrate the product of an algebraic differential form by the exponential of an algebraic function. And here, this approximation sign hides the complexity that so it's not clear when this integral converges and how it depends on omega and on sigma, and for the moment I'm not going to make this more precise, and I'm just going to give some examples. But these exponential periods, so they form a countable subring of the complex numbers, which are similar to the ring of periods, and that we would like to understand. That contains a lot of interesting number theoretic information. And maybe the first question is why should we do this? Why should we care about this? Why should we take the exponential function in the mix and not some other transcendental function? And maybe the first answer is there are some very interesting examples of this. So let's see some examples. So first of all classical periods are exponential periods. So in this talk, classical periods refers to the usual notion of periods, and exponential periods to this generalization. Then, of course, because we have introduced the exponential function, we add Euler's number E, and more generally the powers, algebraic powers of E. Then, for instance, we have Gauss's formula, which tells us that famously tells us that this integral is square root of pi. So, or in other words, it's also gamma of 1/2. So the square root of pi is an exponential period which is not expected to be to be a classical period, for instance, because it would mean that it's a weight 1/2 to correspond to a period of a motive of weight. Well, yeah, it's not expected to be a period. We have, in fact, all other rational values of the gamma functions are exponential periods, and you can see this with this integral representation. And in this case, we're still quite close from classical periods, because it's well known that some power of all these rational values of the gamma functions are classical periods using the beta integral. But there are some maybe more exotic examples. So, for instance, algebraic values of Bessel functions. And so here is one example of a Bessel function, which is written precisely as an integral of this, as an exponential integral. And one more also very maybe exotic example is this Euler-Mascheroni constant. So which a priori is just defined as the approximation of the logarithm by the harmonic series and taking a limit. So this doesn't look very algebraic at all, but it turns out to be an exponential period, and it can be written using these integrals. And in fact, it's also true that the Euler-Mascheroni constant is a derivative of is a special value of the derivative of gamma. And in fact, all derivatives of gamma and all the rational values are also exponential periods. And then there are many others. And but okay, that's maybe a first selection of interesting examples. And I mean, as you all know, and probably this theorem has been quoted many times in this seminar already, but classical periods occur as matrix coefficients of the Grothendieck period isomorphism. So between the Rham cohomology and singular cohomology after extension of scalar. And as you know, this comparison isomorphism is essentially given by integrating algebraic form on cycle, and this formula, of course, is not literally true, but it's literally true for a smooth affine variety, and then it's kind of extended by in various ways. So the first task is to give to put the theory in the same footing as the classical one, is to give a cohomological interpretation of exponential periods. And for this, we turn to, we need some cohomology series first. Two. Before we start comparing them, we need at least two of them. So let's see what this is about. So because we have this additional function, the basic geometric object of the theory are not just algebraic varieties, but what's called a variety with potential, so which is just a fancy word for a pair of a variety and a function. And a morphism between such pair is just a morphism of the underlying varieties, which is compatible with the two functions. And so this is just if you want, it's a comma category. It's the category of variety over A1. So this is nothing complicated, at least just the definition. But we think of classical varieties as varieties with potential via this embedding. So we send the function to the function with we send the variety to the variety with the constant function 0. And the basic observation is that classical veil cohomology theories, so such as Betti cohomology, Rham cohomology, and also LNE cohomology in under some restrictions, extend non-trivially to varieties with potential. And here, non-trivially means not just that you get, you can extend the theory, but the resulting extension, the resulting exponential cohomology series, behave in a way which is really new compared to the and one manifestation of this was that instead of just periods, we will get these exponential periods. So let's look at the Betti side. So here the field is the field of complex numbers, and we can take any abelian group as a coefficient. So what we do is we take, so for any real number, we can look at the half plane of in the complex plane with real parts greater than little r. And using this, we can define the rapid decay cohomology groups of a variety with potential as so co-limit over R of certain relative cohomology groups. So you take the relative cohomology of X, or sorry, this would be X of C, and relative to the pre-image of this half plane. So maybe the first remark, this co-limit looks a little maybe unwieldy, but in fact it's always realized. And in fact, so what happens is that for R large enough, all the restriction maps in this system are isomorphisms, and you can even write it even more maybe concretely as, so this rapid decay cohomology is the cohomology of X relative to any fiber for any Z with real part of Z large enough. But with the only caveat, of course, that the large enough here depends on X and F. So in some sense, this rapid decay cohomology is the cohomology of X relative to a kind of generic fiber of F. Or maybe a fiber, maybe better fiber at infinity of X in the complex plane. So if you take a constant function, so for instance 0, which is somehow the way that we embed varieties into varieties with potential, you just recover the singular cohomology of X, because this thing becomes, sorry, this pre-image becomes empty. And the theory extends with a very similar definition to pairs. I mean X, Y, F. So here Y is just a closed subvariety of X, but I will ignore this. I mean, as you know, for the theory of periods, it's quite important to allow cohomology of pairs, and it's the same for exponential periods, but just I omit this to keep the notation in mind. So let's look at some examples, and the first one is just the affine line with the function x goes to x to the n, and we'll take n at least 2. So if you look at this pre-image of this half plane, you get something like this. You get something which is concentrated on the axes which are given by the nth root of unity. Yeah. So that's this pink subset, and so we're looking at the relative cohomology of the plane with respect to this pink subset, and for R large enough. And here you don't need R to be very large actually. As soon as you kind of separate those blobs, you're good. And it turns out then that there's only H1, the H0 and H2 vanish, and you can write this. I mean, you can choose a basis of the dual space or the corresponding homology group given by this something like this. So you cycles like this, and so on. And this the group that you get is n-1 dimensional. And once we do this comparison, once we have the Rham side and the comparison theorem, this motive, this cohomology will give rise to the rational values of gamma as exponential periods. Another example is this Bessel example, which so here you look at GM with the function x minus 1 over x, or any non-zero multiple of it, and here again you have, so if you look at this pre-image, you have these two pink regions, and this rapid decay cohomology again is concentrated in degree 1, and it's 2-dimensional. And again, you can take a dual basis of these two cycles. And so in particular, this gives rise to algebraic values of Bessel functions. Now let's look at the Rham side. So for the Rham side, you have a field of characteristic 0. As usual in the Rham theory, it's only easy to define in the smooth case, and for non-smooth varieties you have to use various tricks to extend it. So let's start with a smooth variety. So and a function, and then you have the exponential integrable connection or exponential D module, which is simply the trivial line bundle OX together with the connection given by d minus wedge df wedge something. So this is just as a connection, as it's the thing which on local section sends omega to d omega minus r. Sorry, this should be df wedge omega, of course. So this integral connection gives rise to a de Rham complex, which in fact is just a twist of the de Rham complex. So the sheaves in the complex are the same, are just the sheaves of Kähler differential, but the differential is twisted, and in fact the formula here is valid for at every step. So you just take the classical de Rham differential d of omega, and then you take minus df wedge omega. This gives rise, so then you can take the cohomology of this this twisted de Rham complex, and you get what's called the exponential de Rham cohomology, or the twisted de Rham cohomology of the pair. And then this can be extended to all to non-smooth varieties. So the first remark is that these exponential connections, they are all obtained in fact by pullback from a universal one, which is the one which lives over A1. So this E of identity, which is so O of A1 and D minus DT wedge something. And so if K is the complex numbers, then you can look at the solution of this collection, and in fact it's a trivial local system. I mean, by its you can, I mean, this connection clearly is the differential equation which gives rise to exponential of f. So the solution is just a trivial local system of rank 1 generated by this exponential of f. And because it's a trivial local system, this is a manifest failure of the Riemann-Hilbert correspondence, because we always get a trivial local system, whereas these connections is in general not at all a trivial connection. So, and this comes from the fact that this connection, this exponential connection, has irregular singularities at infinity. So the classical Riemann-Hilbert correspondence for regular singular connection does not apply. And so let's revisit these two examples. And in this case, it turns out that, for instance, if in this case for this differential is actually injective on omega 1, and so you just is injective on functions precisely because the exponential is not algebraic. So then you just have to look at the co-kernel on to compute the H1, and you get so one choice of basis is simply dx x dx and xn minus 1 dx, and you do the similar computation for in the Bessel case. So at least we get spaces with the same dimensions, so that's the first good sign that maybe there is a possible comparison here. Now, just to complete the picture a little bit, even though that's not the focus for today, I just want to talk briefly about the Lehalleur case. And here the situation is, well, a little more maybe complicated than the classical Lehalleur setting, because first of all, we have to work in positive characteristic. And so then we fix some for our coefficient, we fix some prime number different from the characteristic as usual. And then if you fix, then there's this additional choice of a non-trivial additive character of FP, so with value in QL bar. Or I mean, you can't work with QL. You have to choose some. You have to at least have a p minus 1. No, piece root of non-trivial piece root of unity. And then you get this Artin-Schreier. I mean, from this additive character, you can construct this Artin-Schreier sheaf, which is a rank 1 QL-adic Lie sheaf on A1. And then you can somehow play the same game. You can define the twisted L-adic cohomology as the étale cohomology with value in this L-adic sheaf, which you obtain by pulling back the Artin-Schreier sheaf. And these cohomology groups, they come up naturally in the study of exponential sums over finite fields, so for instance, like Klosterman sums. But again, yeah, that's not our focus. But also, I mean, this is yeah. Now let me explain a kind of more uniform interpretation of this cohomology theories. via the Fourier transform, and this interpretation will motivate the construction that we'll do at the end of for exponential motives. So I will take a uniform construction, so for the Rham and the Lehalleur setting, but in fact you can also do the rapid decay cohomology, but then you need some more technologies, and I will comment on this later. But for now, let's focus on the Rham and the Lehalleur setting, and if you want, you can really just think of the Rham setting. So we need a kind of, because now we want a sheaf theoretic interpretation of the story. So we need some kind of sheaf theory, and the sheaf theory in the Rham setting will be holonomic D modules, and in the Lehalleur setting will be QL bar adic sheaves. And the important point is that in these two theories we have a distinguished object on A1, which I want to call an exponential kernel. And so, for instance, in the Rham setting, it's this exponential connection E of identity, which I sort of singled out, which is the one from which you can obtain all of the other exponential connections by pullback. And in the Lehalleur setting, it's an Artin-Schreier sheaf with a choice of additive character. So now let me recall the definition of the Fourier transform in this setting. So the sheaf theoretic Fourier transform. So for this I need the multiplication on notation for the multiplication on, so from A2 to A1, and okay, later I will also need for the notation for the structure sheaf. The structure map of A1. So the Fourier transform is in this context is the functor. So from sheaves on A1 to sheaves on A1, which is obtained by you pull back your sheaf to A2 via the first projection. You tensor with the pullback of M. And then you push forward with respect to the second projection. So this is the usual way to construct kind of integral operators from kernels. And okay, there's a shift to I1, but that's not very important. And this construction, so in the Rham context, is what usually called the Fourier Laplace transform, and in the Lehalleur context is the Fourier Deligne transform. And one of the theme of our story is that they are very similar. I mean, there's kind of a uniform structure underneath, so that's why we do it side by side. So now we have a lemma, which so it's probably somewhere in the work of Katz, but it's certainly stated explicitly in the work of Kontsevich and Zeubelmann, and that was one of our main inspirations for this story. It's all good. So we take a variety with potential, and so we write pi for the structure map. So first of all, we can write the cohomology. So either the twisted the twisted Rham cohomology or the twisted Lehalleur cohomology. Well, first of all, we use the push forward and the pullback functor to write it like this. I mean, this is simply this is essentially the definition of that we had. For instance, in the Lehalleur setting, it's really very close to the definition. But the interesting part is that we can write it in terms of the Fourier transform. So what you do is you take the unit object, so let's say the trivial constant sheaf on your x. You push it forward with respect to the function f. Now this object is a sheaf on A1, which doesn't have to be a local system. It can have, because f is not assumed to be smooth, so this can be quite nasty. Then you take the Fourier transform, and then there is this kind of very nice thing that this Fourier transform is actually it's not at all it's not at all badly behaved. It's always a local system, at least outside of zero. And so in particular, it's quite reasonable to take its fiber at any point, and you can choose that, for instance, the fiber at 1. And it turns out that this is canonically isomorphic to the cohomology of this pair. So that's one thing. And the other thing is that now if I start with some sheaf on M, and I take I take the Fourier transform, I take the fiber at 1. This operation, which as we have seen, when you apply it to the push forward of via f, gives me the cohomology that I'm interested in. This only depends on the class of this sheaf M in the quotient by the Verdier quotient by constant sheaves. So this just means that if I take a constant sheaf and I take its Fourier transform, then actually the fiber, this local system that I was talking about out is on GM is 0. Which is, I mean, it's the usual property of the Fourier transform that somehow it exchanges constant sheaf with Dirac's at 0. So that's what's happening. And another way to think, about this quotient is to look at the. So yeah, there's another realization of this quotient as instead of a quotient as a subcategory of the category of sheaves on A1. This is just the subcategory of sheaves on A1 which has a trivial cohomology. And well, the precise statement is that if I take sheaves on A1 with trivial cohomology and I include and then I pass to the quotient, the resulting functor is an equivalence. And this is essentially the picture that we will lift to the motivic setting. But this will come later. Okay. So that in Kontsevich and Soebelman, they use it to define to do some kind of odd theory with this in this setting. So to define what they call an exponential mixed odd structure. So I'm not going to go into that, but that's essentially taking this last lemma and putting it into the theory of mixed odd module of Saito. And yeah, as I said, it's really the basis of our approach. But so let's come back to periods. And now we have all the ingredients to state the comparison theorem between which gives rise to exponential periods. So we take a subfield of C. So we have this comparison theorem, so which has been worked on in various cases, various levels of generality by many people, starting from a letter of Deligne a long time ago, and some of the final version, or the version that really gives a comparison theorem for all varieties is due to In and Roux-Carroll. So it's really the same as Grothendieck's theorem, except that we add a function, and we, instead of working with the Betti and the classical Betti and Rham cohomology, we work with these exponential versions. So there is a canonical isomorphism between the Rham cohomology. So now also with pairs, and it's twisted by a function. After extending scalars to C, is the isomorphic to the rapid decay cohomology after extending scalar to C. And again, so this is given morally by integrating this by this kind of integrals, and this is literally the case for an affine smooth variety. So in particular, let me comment that this definition of rapid decay cohomology and this condition on the real part going to infinity is exactly necessary to ensure that this exponential decreases and this integral converges. So that's why it's there. Yeah, and I should say that this is really not. I mean, already Grothendieck comparison theorem is quite difficult, but this is I would say even more difficult. I mean, because it doesn't. Well, I don't know. It involves more analysis, or more real analysis. In particular, it involves construction like real blowups. Yeah. So now if you have an algebraic extension of Q, you define an effective exponential period as a matrix coefficient of this comparison isomorphism, and then exponential period, general exponential periods, as in the classical story, are obtained by inverting 2πi. So just multiplying by powers of negative power, possibly negative powers of 2πi. So this is a cohomological definition of periods, and so I haven't given you a more elementary one. And from the Kontsevich-Zagier perspective, you would expect that there is an elementary definition, but it's actually surprisingly subtle, and this has been explained very clearly. But I mean, it's really an non-trivial story in 2 papers by Johan Comelin, Philippe Aveger, and Annette Huber. So they compare a naive definition of periods, the cohomological one, and some other ones. So it's really quite a nice story. Okay, so now once you have a notion of periods, you can try to formulate some version of the period conjecture, and this I will start with a very vague one, and this will maybe not tell much, but and so for classical periods, this is the conjecture due to Grothendieck and Kontsevich-Zagier, and in the exponential setting, it has been stated precisely. I mean, more precisely than what I'm doing by Fresãs and Jossen. The first part is that some of all algebraic relations between exponential periods or exponential periods should be explained by algebraic geometry. So, for instance, by change of variables, by morphisms of varieties, or morphism of variety with potential, by the Stokes formula, and this should be more precise in the sense that if I have if I look at relations between exponential periods on 2 varieties, I should be able to explain them in terms of somehow the geometry generated by x and y. I shouldn't have to go much beyond x, y, their powers, and the kind of things that I can obtain from x and y in some sense to explain those relations. So now, before I come to motive, I want to talk a little bit about families, because I think that's an interesting aspect of the story. So classical periods, they often occur in families, in the sense that classical periods often occur as special values of period functions at algebraic points. And here, so the period functions are functions that you obtain when you look at the variation of cohomology in an algebraic family. So you look at the comparison isomorphism in fibers of a family of algebraic varieties, and you obtain varying periods, and so that's what I call very roughly a period function. And it's known that it's well known that period functions on curves, so in dimension 1, they satisfy Picard-Fuchs equation. I mean, that's essentially differential equation. That's essentially the definition of Picard-Fuchs differential equations. So which are in particular linear differential equations with regular singularities. And these regular singularities this is of course the start of a long story of regularity in the context not just of differential equations on curves, but also on D modules in higher dimension. And just to see one example, so possibly one of the most classical example of periods, so elliptic integrals. It's well known that this function satisfies the differential equations with regular singularity as 0 and 1 and infinity, which is given here. Sorry, this is very weird. Similarly, there is a parallel story in the exponential setting, which I mean mostly remains to be explored. But there are also this exponential period function, and they will also satisfy a linear differential equation. But there, the singularities are not regular in general, and ultimately this is because the exponential function has irregular singularities. And as an example, we have this Bessel function. So the Bessel function gives, given by the definition from the introduction, this gives an exponential period function on GM, which satisfies this classical Bessel differential equation, which has an irregular singularity at infinity. And just as a general kind of philosophical remark, so it's known in the classical analytic setting. So just forgetting about the algebraic geometry and just thinking about complex analytic geometry, that these exponential connections are actually the building blocks together with regular singular connection. They are the building blocks of general meromorphic connections or holonomic D-module. So, for instance, the first instance of this at the level of some formal level in dimension 1 is the Level-Turretin theorem, which tells you how to a connection on a formal disk or formal pointed disk decomposes as after maybe a ramification, decomposes as a sum of tensor product of exponential connection and regular connections. But this turns out to be true really much more generally and much more. So in particular, there's the Kedlaimo-Chizuki theorem, which gives a kind of very general structure theorem for meromorphic connection in terms of regular singular connections and exponential connections. So this is just to say that these exponential connections sort of, yeah, even maybe at the beginning it seems a bit arbitrary, but they are, I think they are really fundamental from the point of view of general differential equations. And one motivation to study this family of varieties with potential and exponential motives is that they give algebraic geometric incarnations of certain differential equations with irregular singularities. So they allow to go beyond the case of regular singularities. Now, I want to talk a little bit about the general picture of periods and motives. And yeah, the idea is that the theory of motives can be used to give a precise formulation of this very vague period conjecture that I've stated before, and these precise formulations then lead to structural predictions in transcendental number theory. And so I will give a kind of an outline of what can be done using let's say Nori motives, both in the classical setting and the exponential setting. So really the series are really parallel. So from this kind of formal machinery of Nori motive, you can get the following. You can get a Tannakian category of mixed motives, so with rational coefficients over k, which in particular contains objects which are associated to each cohomology groups of pairs of varieties or pair of varieties with potential. Because it's a Tannakian category, there is an associated motivic Galois group. So this is really a huge pro-algebraic group over Q, which seems very unwieldy at first. There is not, and so this motivic Galois group, you should think of it. It's the fundamental group for the fiber functor, which comes from the Betti cohomology. So this is in some sense purely on the Betti side, but there is also from the comparison between Betti and the Rham, there is a motivic period torsor, which is it is really it's an algebraic variety or a pro-algebraic variety over Q, which is a torsor over the motivic Galois group. Then there is an integration morphism from this motivic period torsor to classical. To periods, so either classical or exponential, but really just the numbers. And so you should think of these you should think of this motivic period torsor as being sort of formal motivic periods, and this integration map takes a formal periods and integrates it and gives you and this formal period you could think of as a class in the Rham cohomology, a class in Betti cohomology, and then you integrate it using this your usual integration pairing. And the first formulation of the period conjecture is that this integration is okay. I mean, this is a little bit this is a little bit imprecise, but let's say that it's essentially what you want is that all relations between classical or exponential period are reflected at the level of so this should be the function on the period torsor, not the period torsor. This was already the case here. Sorry, this is so it's from the function on the period torsor to the period. So this version of the period conjecture, because it talks about the full period torsor and the full Motivi-Galois group, which are sort of this infinite dimensional object that we essentially don't understand, it's maybe not so useful to give a precise statement. But it turns out that, and this is maybe the more interesting part, is that you can also cut finite dimensional parts of the story for every object for every motive. And so in particular for every cohomology group of an algebraic variety. So for every object, you have a Motivi-Galois group for this object, which is it's a finite dimensional quotient of the full group. And you have also an associated period torsor and an integration morphism. And then you have the second version of the period conjecture, which is a version for a fixed M. And the advantage of that version, sorry, I'm going a bit fast, but maybe it's not, these formal aspects are not so interesting, but maybe the point I want to make is that this version with a fixed motive is equivalent to a conjecture on transcendence degree of fields generated by periods, so the classical formulation of the Grothendieck period conjecture. And because then you have finite dimensional algebraic groups, you can talk about dimension, and this is the part that really leads to predictions about transcendence. So I mean, if you've seen this kind of formalism before, you probably know that from the classical period conjecture you can get precise predictions about transcendence. Of course, then proving them is a much harder business, but at least this gives you a structural way to generate conjectures about intranscendental number theory. And so this program that basically I've outlined, it has been so this construction of these categories of mixed motives, Motivi-Galois group, period torsor, and so on. This has been realized. So for the classical setting, so this is you can work. I mean, you have these two theories, sort of competing theories of mixed motives, which are due to Nori and Voevodsky. And so for the Nori theory, this idea that you could use Nori motif to state and reformulate the period conjecture is due to Kontsevich. And then it was put in a complete. It was completed by Annette Huber and Stefan Mullerster. And in the Voevodsky setting, so from Voevodsky motif, Ayub also developed a formalism in the sort of another version of this whole story, and the fact that they give the same group and the same period torsor, so isomorphic Motivi-Galois group and isomorphic period torsor was proven by Choudhury and Galois. So now in the context of exponential periods and exponential cohomology theories, a theory of exponential Nori motif has been developed by FresÃ and n-Jossen. And now we can state one of the main goals of our project, which is to develop a theory of exponential Voevodsky motifs, and to use it to also develop a theory of to relate to the theory of exponential periods, and also hopefully to compare it with the theory of FresÃ and n-Jossen. Yeah, so this is just to illustrate the kind of so from the context of exponential Nori motifs, you can use this period conjecture to really make some predictions. And for instance, you can recover the prediction that the Lindemann-Weierstrass theorem should be a theorem. So the Lindemann-Weierstrass theorem tells you that the transcendence degree of exponentials of algebraic numbers. And this is predicted. I mean, the statement is predicted by a very special case of the exponential period conjecture. You can also recover the conjecture of Lang on the transcendence of rational value of gamma, and also statements such as, I mean, many exponential periods. Then the exponential period conjecture predicts that many exponential periods, such as the Euler-Mascheroni constant, should be actually algebraically independent over classical periods. But there are more examples of this, and you can have a look at the book in preparation by FresÃ and n-Jossen for more examples. Okay, so in some sense that was all background for what we do, but now to explain what we do, I have to. So the construction builds on the theory of Voevodsky motives. So I have to give a very quick introduction to that setting. And for construction, we really need not just Voevodsky motives or a field, which maybe you have seen, but the theory of a general base, so which we can think of as Voevodsky motivic sheaves. And so what this looks like is that for essentially any base scheme, we have a triangulated category of mixed motivic sheaves. And by construction, so I'm working with a Q-linear version, so it's Q-linear, and it has a tensor product. So I will not give you the full definition, but you should think about it like this. So in some sense, it's quite a formal construction. So you start with all smooth schemes over S. Then you look at the category of étale sheaves on smooth schemes over S with étale sheaves of Q vector spaces. So that forms an abelian category, and you can take its direct category. And then the category Dm of S is obtained from this by by imposing somehow formally some relation. The first one is you impose A1 homotopy invariance. So you force the A1 times X to be isomorphic to become isomorphic to X. Because this A1 homotopy invariance property is shared by many cohomology theories that we're interested in. I mean, of course, by Betti and Rham cohomology in the context of this talk, that's important, but also for Chow groups of smooth varieties. And then the second step is that you invert Tate twist. And again, if you're familiar with the theory of, for instance, pure motives, you know that this is a very natural step. So the motive of P1, or let's say the reduced motive of P1, is not invertible for the tensor product, and you have to make it invertible to get things like Poincare duality. And so this is something that you impose formally. And so it is. I mean, of course, to be able to do these two steps, you need some tools from homological and in fact homotopical algebra. But it is a very formal construction. And what is maybe surprising is that it still has some. You can prove things about it. Let's say. And so one of the things that you can prove, and that's really not at all a trivial thing to develop, is that there is a 6-operation formalism, so that these categories of motivic sheaf behave in very similarly to other sheaf theories that are more classical in algebraic geometry, such as L-adic sheaves or holonomic D modules. And what this means, I mean, again, in very condensed form, it means that if you have a morphism of schemes, you get two adjunctions. So a pullback and push forward adjunction, which is sort of familiar from just usual sheaf theory, and also this sort of exceptional functoriality. So this F lower shriek and F upper shriek. Which encode rather, so for instance, F lower shriek encodes relative cohomology with compact support, where F lower star encodes relative cohomology, F lower shriek encodes relative cohomology with compact support. And you may wonder why there isn't a somehow derived sign everywhere. So this should be R F lower star, but in fact all the functors are automatically derived. And this is I mean, part of the problem is that we don't know how to write this as the Dirac category of an abelian category in the way that we hope is possible. I will just say something later about this. But so nevertheless, you have these 4 functors, and the other, I mean, it's 6 functors. So the other 2 are the tensor product, and there's also an internal arm, also as kind of familiar from sheaf theory. And all these functors satisfy a lot of properties, which are sort of the usual properties from the theory of sheaves on manifold or L-adic sheaves or holonomic D-modules. So things like proper base chains, projection formula, projective bundle theorem, Verdi duality, and so on and so forth. And not only is the theory formally parallel to these more classical sheaf theory. In fact, they are related to them via realization functors. So, for instance, in the Betti setting, so if you take a finite type variety over the complex numbers, then you have a Betti realization functor from these motivic sheaves to classical sheaves. So here it's a little okay. This notation seems a little weird, but what I mean is you take the algebraically constructible sheaves on S, then you take the category of you take the incompletion, and you take the Dirac category. But you can just think of this as the Dirac category of it's closely related to just the Dirac category of all sheaves on sheaves of Q vector spaces on S of C. I just write it like this for later, just to make a correct statement later. Then, so there is also a Rham realization. So although this is not, I mean, there are some serious technical difficulties actually to make this work, and so there is. So there are many partial results on the Rham realization, but there's also a work in progress from Brad Drew and Martin Lehalleur to construct a Rham realization functor. And here the situation is you have a finite type variety of a field of characteristic 0, and then you get a functor from these motivic sheaves to the Dirac category of Dirac category of the in category of holonomic D modules over S. And so both realization functors commute with the SIG functors and here this has to be taken with a grain of salt. But let's say that in most cases it commutes, and in particular, so this is unconditional for the Betti realization, but this is the part that's quite difficult to obtain for the Rham realization. So there are constructions, but to obtain a construction which is compatible with the SIG functor is so this is part of this work in progress of Drew and Lehalleur. And so it's expected as well that but this is really not. This is still open. That once these two functors are properly constructed, that they will be compatible with the Riemann-Hilbert correspondence. That you can really that you get a commutative diagram like this after extending scalars to the complex number. But anyway, so this realization functors and the existence of a diagram like this is at least none of a field where these categories just become Dirac category of Q vector spaces and Dirac category of K vector spaces. And these two realization functors and the comparison between them, this for the category of motives over a field, this really underlies Ayub's approach to periods, which I've mentioned before. So I just want, as I mentioned before, the major differences between these motivic sheaves and classical sheaves is that unfortunately we don't have the abelian category of motivic sheaves, and of which this would be the Dirac category. And in some sense, this is really one of the major open questions about Voevodsky motives. So this is sometimes called the motivic T-structure conjecture. And so this causes many difficulties, but so yeah, in some cases you can still do things. Okay, so now I have 5 minutes to tell you about exponential motives. But at least all the ingredients are really in place, and you will see that everything should fall together. So we really take inspiration for these ideas of Katz and Kontsevich-Zagier. So we define the category of exponential motivic sheaves on a scheme S as the category of schemes on the category of classical motivic sheaves on A1 times S, which satisfies this condition that. So in Kontsevich-Zagier it was P lower star. Here we put P lower shriek for. I mean, it's more convenient in this in families. But it's it's just the dual condition of Kontsevich and Zagier. And again, you can think of, in fact, of this thing. It's also equivalent to the Verdier quotient like this. So motives on A1 modulo some constant motives, so motifs which come from the base by pullback. And so by construction, this is a Q-linear triangulated category. I mean, this condition is triangulated. Sorry. What is not so clear is the maybe the maybe I will skip this remark. It's a little let me just mention that there is another possible approach to exponential motive, which the idea would be to start instead of, to try to adapt directly the Voevodsky construction of DM, but working with varieties with potential. And so this has been studied by Marco Roballo, but it's not published. And it would be very interesting to compare the two, but it's really not clear how to compare the two. But yeah, I think maybe it's reasonable to expect that you get the same answer. The most interesting part of the structure is the tensor structure. So it's not given by it's not the tensor product which come somehow from the motives on A1. It's given by convolution product. So it's additive convolution with respect to the addition map on A1. So it's given by a formula. If you take your two exponential motifs, so those are two things on A1, you pull them back with respect to both projection, you take the tensor product. So this is an exterior product, if you want, of M and N, and then you take you apply this some lower shriek functor to it. And what it turns out to give you a symmetric monoidal structure on this category, and in fact it's even a symmetric monoidal infinity category. But this is kind of more technical aspect. So what happens in this category is that we have exponential objects which play the same role as the exponential connections that we've seen many times in this talk. Namely, maybe it's a little technical. So it's you can define them. Let me just show you the formula So it's a formula. It's something defined using the sixth operation formalism for classical motives. But the important thing is that, well, first of all, so for any function on x, I get an exponential motive EF. It satisfies this property, which is, it's the analog of the functional equation of the exponential. That exponential of f times exponential of g is exponential of f plus g. And exponential of 0 is the unit, as you could expect from the exponential function. Exponential of 0 is 1. But then using this object E0, you can actually express there are two interesting functors. So first of all, there is a faithful functor from classical motives to exponential motives. So we expect that. We want exponential motives to be sort of an extension of classical motives, and this is what happens. So at least you have a faithful monoidal functor like this, which is defined in terms of convolution using this E0. And the inclusion on the other hand, the inclusion of exponential motives into this larger, this is by definition, this is defined as a subcategory of motives on the affine line times affine line over S. This admits a right adjoint, which is simply given by convolution by E0 as well. Okay, so let me state the main theorem, which is that this construction of exponential motive admits the same rich functoriality as DM. So this is not a precise statement, but there's an underlying a precise statement, which I won't give. But this means that we have these functors f upper star, f lower star, f lower shriek, f upper shriek for morphisms of schemes, and they satisfy the same properties as the same kind of properties as that I alluded to before. Okay, and the functors are actually pretty explicit in terms of the functors, but let me just skip that. Oh, and I should say that the tensor, in particular, as I said, the most interesting part is the tensor product, and the tensor product is this additive convolution that I mentioned before. Yeah, so now you can attach exponential motives to varieties with potential using these two ingredients that I mentioned. So this exponential twist, this EF, and the new functors, like for instance this push forward. So the cohomological motive of a variety with potential is just you take the associated twist for F, which is an object which lives on X, and then you push forward to the base. Okay, I will skip this example. Yeah, so the rest of the talk is a little more sketchy. So there are some details which remain to be checked, but just to explain the relationship with periods. So first of all, we have to assume the existence of this Rham realization for DL, but as I said, so it's in good it's in progress, but then it looks very promising. Then we use the Fourier transform for the modules, and also for this theory of enhanced sheaves for the Betti side. We need a kind of Fourier transform which is available now, but it's a little technical. But from this you can construct Betti realization functors and Rham realization functors over a field at least. And the reason that you need, well, okay, so, and these realization functors have somehow compute the correct cohomology. So if you apply them to the motifs that I mentioned before, they recover the rapid decay cohomology and the twisted Rham cohomology. So now it remains, and that's really not done. It remains to compare the two and to use this to develop the theory of periods following the Ayoub's template for classical motifs. Okay, and there's also a Fourier transform in this setting, which is okay. I just finished by saying that you can then copy. Now you have the exponential kernel, which is E of identity, which is an exponential motive on A1, and then you can just copy the definition of the classical Fourier transform, and you get essentially now you get a lift. I mean, should be a lift of the Fourier transform for the Rham realization once we know it exists. And this is really a functor that doesn't exist at the level of the n. Okay, maybe let me stop here.
All right, thank you very much, Simon, for this very nice talk. So let's thank Simon. Do we have questions for the speaker?
Sorry, do you have a text on this matter?
No, I'm sorry. It's still in preparation, but it should appear soon.
Okay, thank you.
Maybe Simon, so in general, your varieties are not compact or complete because of this potential function. And
Yes.
what the most famous conjecture in the classical period context about if there is some relation, there is some algebraic geometry going on, is the Hodge conjecture, which has to do with the cohomology class of algebraic cycle. I mean, is there something similar also in this context? Is it possible to formulate, for example, cohomology class of algebraic cycle and try to formulate a kind of Hodge conjecture here?
That's a good question, and it's not clear to me at the moment. You can write down a type of motivic cohomology from in this theory, just as morphism groups in this category, and you can express them in terms of classical motivic cohomology. And then from using the realization functor, you can get a map to various cohomology groups. But I really don't know the analog of the condition of being a notch class. But maybe for people who have studied this Kontsevich-Zagier exponential mixed theory, this could be clear. But I don't know this so well. I've just taken it as an inspiration, but I haven't looked at it so precisely.
I will stop recording and then we go to that informal